I'm presenting with Kris Jusiak on adapting ranges algorithms for most metaprogramming needs in fewer than 1,000 lines of code. For those of you who have seen my talks before, my cute trick talks or whatever, this is kind of like that, except for the cute trick we're explaining is essentially an actual real practical tool that can use ranges for most metaprogramming, which is pretty amazing. So yeah, if you are in the back, it's probably good to pull up the slides. If you have a laptop up at all, it might be good to pull up the slides because there's a lot of code here. But I'm going to try and go at a pace and explain everything such that most people attending this conference should be able to follow most of this talk. But why are we even trying to talk about this? So to be perfectly clear, in most software engineering scenarios, metaprogramming is just completely unnecessary, and it can sometimes be actively harmful to the life of your code base. So, like, write a design doc before you put metaprogramming into your code base. Like, get approval from your colleagues, work through it, understand maintainability trade-offs. We do want to talk about the best ways to do some metaprogramming tasks if you have to. But also, there's quite a bit you can learn from regular programming use cases, programming use cases from messing around with metaprograms. And to be honest, like, at least I find metaprogramming quite fun. I think it's this little corner of functional programming for C++ programmers or for naturally functional programmers who got lost and ended up in C++. So, disclaimers. Parts of this talk poke at the extreme boundaries of compiler correctness. Compiler authors are writing compilers for real code. They are optimizing their bug queues for real code use cases. Many of these extreme metaprogramming use cases don't come up in real software engineering scenarios, and so they don't get prioritized quite as often as you'd think. And so, yeah, we're running into things that create very strange bugs. I think Eric Niebler, who does a lot of this, tweeted recently that he's filed 63 GCC bugs in the past 2 years or something like that. That's not uncommon for the people who do this kind of thing. As far as we can tell, everything in this talk is well formed according to the C++ standard. We have talked to people about most of it. We'll let you know if there's anything that we're not completely sure about. That doesn't mean that they work on all current compilers or that they ever will, right? I'll definitely point out some interesting cases where there's things that are in there that if you change them very slightly to something that's exactly equivalent according to the standard, you get a completely bizarre error message. So this is like heavy disclaimer. This is technically C++, but it may not actually be helpful. So yeah, in other words, to quote LLVM, here be dragons. I'm sure it's quoted from somewhere else, but that's where I know it from. So this kind of started when I posted last July this cute, well, it started for me when I posted this cute C++ trick, and don't worry about trying to read it. I'm going to show it on the next slide. I kind of set this challenge for myself to use a regular std sort to sort a type list. If type list doesn't mean anything to you, don't worry, I'm going to explain it. But the basic idea is, like, can we use regular C++ algorithms for metaprogramming? And it turns out that Kris had been working on this already and had done a much better job of it, much more thorough job of this, and uses basically the same trick to access all of the ranges algorithms with these very simple ranges. Simple is a stretch, but clever, let's say clever, range adapters that basically just use the ranges algorithms directly, right? So it's the same idea, but generalized beyond just sort. So we're going to first walk through the actual cute trick here that explains the sort, and then Kris is going to get up and show how it generalizes to all algorithms that interact with ranges, and some actual practical use cases that I actually think are pretty cool and are things that I've done in real code before. So yeah, let's dive right into it. So don't try and understand all the code on the screen unless you're here for exactly one piece of this and could figure out all the rest of it in your head, which there are people probably in the room who are like that. But this is more or less the summary of the trick I'm going to describe, and I'm going to build it up. We're going to go through each piece of this. I think there's like 10 different like mini talks that build this thing up. So, but let's first talk about type lists. So type lists are something that people have done in C++ metaprogramming and in general in any metaprogramming in any language for a long time. It's like just a basic data structure of types. With C++ 11, we got this variadic template parameters, right? Variadic packs. And that's basically a compile time data structure, right? It's a list. And so Eric Niebler made this really good point way back in 2014 that like now that we're in C++ 11, which back then was brand new, we have support for a native data structure for type lists, and we would be foolish to work with anything else. So yeah, the basic idea behind this is my who in here has a favorite class template? Is anyone nerdy enough to admit they have a favorite class template? Oh, wow. Okay, you're in the wrong conference. So this is the full declaration and definition of my favorite class template. You ready for it? There's a semicolon there. It's empty, open, close braces, right? You don't even need a name for your template parameters because you're not using them anywhere, right? That's it. That's the definition of a type list. Everything else is just algorithms on that, right? It's just a convenient way to get back to this native C++ compile time data structure, right? The ... the parameter pack is the native compile time type list in C++. And you can use it with algorithms like this, right? We're just using this as a way to pattern match so we can pull out the native data structure, right, into the algorithm. So if you had an algorithm like zip, this is how you do that, right? We're using partial specialization to pattern match on these type lists and pulling out the native data structure for compile time programming. So let's talk about what we even mean by a type list being the type domain or type analog of a regular list. So I've already talked about type lists. Obviously, in regular code, an example of a list-like structure is a vector, right? And in the type domain, we have this, a type list, right? Now, this is just a name of a type, right? This is just a specialization of a template that names a type. So we have this distinction between the type and value domain, and I'm going to go through this constantly. So throughout this talk, so people talk about. Let's look at some other data structures. Mappings, std map is an example. Anyone have a guess at what you'd put on the right-hand side of this for the type domain?
List of pairs.
Type list of pairs is one option. There are a number of things that could go here. I have one that I like to put here because it starts to get people thinking about how compile time and type domain data structures work. So I'm going to specifically say type domain data structures to distinguish from like const expr value data structures, right? There's a distinction there that I want to make sure is clear. People say, oh, we have const expr programming, therefore we have compile time programming. No, we don't have value like types, so we can't really do const expr programming with types. Although we're doing it anyway. So here's one example of a mapping. An overload set, right? An overload set is a map between a input type and an output type for each function. So that gives you some of you start getting your brain around what compile time and type domain data structures look like. Function calls Traditionally, in metaprogramming libraries, function calls have looked like this. There have been this colon type member type for the template, right? And we use this in type traits in the standard library, but it's also, goes way back to when people first started metaprogramming in C++. Let's talk about literals. So, the most obvious thing in the type domain that's a literal is just like any kind of type, right? Int, vector, A of B of C, right? That's like some specialization of a template. But there's also kind of this ambiguous like type value domain thing going on, which is where people get very confused about metaprogramming sometimes. Because like integral constant, right, is very clearly in the type domain. It's a type, right? But it's also something most people would recognize as a representation of 42, right? So it's like, and in C++20, actually, we make this even blurrier, right? Because we have these auto non-type template parameters that allow us to make like one wrapper to rule them all, right? If we had introduced integral constant in C++20, we probably would have done this. We just would have said like value wrap or something like that instead of integral constant, because you can wrap any kind of value that can go in there. You can also make compile time strings. There are plenty of talks about that. I won't go into it here. It's just a little bit distracting, but you can definitely search, Google it, ask Jeeves, All right, so here's how much I've explained of the Qt trick so far. Is everyone following? Okay, so I'm mostly gonna try and keep going fast enough that that it makes sense to pause for questions. Whenever you see this progress slide with this word progress on the top, that's when I'm gonna try and pause for questions. There's about 10 of them across my part of the talk. So I tend to go a little fast, I understand, and if I mess something up, we shouldn't be too far ahead to roll back to explain it at a progress slide. Okay, so let's talk about implementing metafunctions and such. So remember that our metafunction calls at the call site looks like this, right? You're getting a type member here, right? Std type identity was added to C++20, and it looks like this. This is like an implementation of std type identity. That is, I would assume, pretty much mostly conforming. Actually, not quite, but yeah, very close. It's missing an underscore in the name, but other than that, yeah, this is basically it, right? So P0887 proposed this. Here's the paper for P0887 to give you some idea of how much work is involved in an absolutely trivial feature, right? This is a labor of love for WD21. You can imagine anything more complicated than this very quickly gets out of control. So if you see Teamer around the conference, thank him for putting in this work. That's like pretty incredible. But even in that paper, it directly mentions the use of this for metaprogramming. The idiom that we are used to is to have this type def type and a member value if we need to get a value, right? If we need to switch back from the type domain to the value domain, then we use a member named value. It's kind of a typical pattern. And there's a number of talks on this. Walter Brown's talk is fantastic, Modern Template Metaprogramming. But gives the exact use case here of inheriting, right? And so if we want to implement something that has a that is like a metafunction that returns a type, right? We can just inherit from type identity. And then we have this open close curly braces that's empty. And this has this really nice property, right? We have this like shortcut, idiom, right? Where we're inheriting from std type identity. But if you actually sit down and count the characters, there's like more characters in this than there is in this. And people are like, well, why would you use a shortcut? Why would you use an idiom if you're having to type more? And that's not what idioms are for, right? Idioms are for communicating information to your reader. And so this inheriting from type identity and then having an empty open close curly braces is a really useful way to communicate to your reader that the only purpose of this class is to be a metafunction, right? And so if you're reading a metaprogramming library and you see this, you know that there's nothing else you have to think about other than what's in between these angle brackets here, right? So this is in general something you should take away from how we should use idioms in C++, right? It's not about saving typing. It's not about ergonomics. Well, not about typing ergonomics. I don't really think we should use that word, by the way, in these discussions because it means different things to different people. But it's not about typing. It's about communicating information to the reader. How am I doing on speed? I'm doing all right. All right. So this is as far as we've gotten. Does everyone understand this so far? Awesome. All right. Let's talk about how we actually get the signature of the metafunction sort that we're writing here. In the cute trick that I gave on Twitter, I used a lambda for the key function. I used a key function, could have used a compare function as the way to make a predicate. It was just easier to fit into the 25 lines that I could put onto Twitter. But traditional pre-C++ 20 metaprogramming convention for predicates was something like this. It was a type that had a FN member alias template. Before that, in Boost MPL, this is a Boost MP11 convention, but before that in Boost MPL, there was a nested member template that was named apply. So there's been several conventions. I think this is the one that's more or less stuck. So if we wanted to, as a user of the library, create our own custom key, we would do something like this, right? We'd have a type that has a nested member type alias that performs the actual function evaluation, right? And that gives us this nice property that our template parameters to our functions are all the same category of template parameter, right? We don't have universal template parameters in C++. And so it makes it really hard to match a template if you have different categories of template parameters in your metafunctions. If that made no sense to you, don't worry about it. That was mostly targeting people who have done a little bit of metaprogramming. But in general, the idea is if you sit down and try and do this at scale with a real metaprogramming library, you very quickly find that it's pretty annoying to have mixed type, value, and template parameters. I know I just said template 3 times in a row. So, but we actually think that in going forward in C++ 20 and greater metaprogramming libraries, a new convention is probably going to develop just because the call site becomes so much cleaner. So we think that predicates are probably going to be expressed as lambdas or callables that take a std type identity wrapped argument and return a type or a value, depending on the context. In this case, we have a sort, so we need to return a value, right? I'll explain the type identity wrapped part in a second, but this is the general idea, is that the call site would look something like this, right? If we had to, remember call site is like a weird word here, right? We're talking about type domain, so call site is gonna look like a type. But if we wanted to sort some type list, which I'm representing with ... I'm gonna do that all throughout the slides because I have all kinds of ... in here that are gonna be explained later. I'm explaining all the ... And our predicate looks like this. And this is actually, if you've ever tried to use a metaprogramming library before C++ 20, this is actually really clean for a custom predicate. Explicit template parameters for lambdas also helps. So lambda is an unevaluated context. Another feature that we got in C++ 20 is these explicit template parameters, which help us do this pattern matching, right? Not pattern matching in terms of a language feature, but in terms of a match. Can I take the question as soon as I get to the progress slide? Thank you. So metaprogrammers are always thinking about this kind of pattern matching. How can I get names for the things that I want to use, right? So you're going to see this as a repeating discussion, right? We need a name for t in order to do this size of t, right? And if we were to just take auto here, right, we would have the type identity of T. We wouldn't have a name for T. So these explicit template parameters allow us to extract a name from a pattern in a way that's really helpful. And you're going to see this over and over and over again throughout this talk, and over again throughout metaprogramming if you do any more of it. So the alternative, if we didn't have this feature, would actually look like something like this, which is much uglier in my opinion, right? We actually have to take the decal type of the value and extract the type out of that and then do size of, right? Because this is the thing that we're actually being able to call T, right? And that's actually really powerful. I hope by the end of the talk that you'll get some appreciation for how powerful that is. Why do we wrap instead of type identity? Anyone want to shout it out?
To prevent deduction.
What's everyone's least favorite type in C++?
Void.
We got there. What if T is void? Then none of this works. I can't, if I didn't have a type identity here, I can't call this function. It's not well formed. But it's not just void. Like there's been several attempts to make regular void part of the standard. And the problem is that doesn't solve all of our problems here, right? What if it's an array type? Or what if it's, in the craziest case, what if it's an incomplete array type? These things are type-ish things that you're allowed to write in template parameters. That, yeah, so there's all kinds of things that this could be that would cause problems. And it's a lot easier to just wrap it in something. Some metaprogramming libraries, instead of using type identity, will create their own wrapper to avoid collisions. I've written one that uses a template named wrap that does this. But it's the same idea, right? All right, here's our progress so far. We now have a signature. All right, question.
So I think I just got my answer on this question. I hadn't seen a lambda passed as a template parameter before, and I was going to ask if that just comes through with auto and the compiler just does its thing. So I think I have my answer.
Yeah.
What does wrapping it in type identity get you in that case with those things where it's not really well defined?
Right. So remember, type identity is this. Let me go back to my overview. It's a really simple type here, right? That just contains an alias, right? So this is a thing we can construct. It's default constructible, it's copyable, it's movable, it's trivial, right? And it still contains the information about the type without ever having to instantiate the type, right? So if T is void, type identity of void is still a perfectly reasonable type that we can instantiate, we can pass around, we can copy, we can assign to. That doesn't mean anything to do that, but yeah. So this is why type identity is pretty valuable here. Perfect. Any other questions? Awesome. Uh-oh. Did I... Oh, getting a parameter pack out of a type list. We already kind of touched on this, and I'm actually just going to skip over this slide very quickly. Right. We already touched on this. Right. We would like to be able to do something like this, right? To be able to extract a name from the type list or something like that. There have been proposals along these lines. They're very complicated, and mostly we've let them rot because they're just too complicated on various axes of specification. But also because you can get the same effect with partial specialization pretty easily, right? So this is the same thing we were talking about earlier, right? We're pattern matching on the type list T's to get a name for our pack, right? We're just getting a name. So there's this repeating theme of getting a name here. And this is how we extract this pack, this native data structure from the type list. Why not write sort to take a pack directly? It's a thing we could do. Anyone have any ideas? So one reason is that, what if we had to take multiple lists, right? We can't just take that directly, and we want to be consistent across the design of a metaprogramming library. But the bigger problem perhaps is like, how would we return, right? You can't just say using type equals t dot dot dot. That's not, there's no real way to give back that pack to the user other than to wrap it in something. So this is the reason why we use type lists, like data structures like this in metaprogramming libraries. All right, another progress slide. How are we? Everyone follow that?
So,
Can you just summarize real quickly?
Sure.
Like with the, just.
Right. So now we are using partial specialization to pattern match on the case where the first parameter is a type list. And in that case, we are going to call the template parameter pack of the type list T's. All right. This is a partial specialization pattern that you see over and over and over again in real code, to be clear, like not even just in metaprogramming. And it's incredibly useful. I think I had my CppNow talk my core C++ talk from last year actually went into detail on all of the mechanisms of partial specialization, if you want to look that up.
Probably a really dumb question, but why are there no parameters to the std type identity that you're inheriting from?
It's a dot 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 that I'm going to fill in.
Oh.
So all the dot dot dots will be explained.
Okay.
So yes, this is not working code. I'm sorry.
No, I was just.
Yeah. All right. So now we're finally ready to start implementing. We are 30 minutes in, and I'm getting there. Okay. We're finally ready to start implementing the logic of our function, right? We finally reached the point where we have all of our names, right? We have our T's, we have our key, and so we're ready to start writing the metafunction body. So general strategy overview, we're going to get an array of indices for our type list. So enumerate, this is called enumerate in Python. I don't think we have a standard name for it in C++, but you basically want a list of, 0 to n-1, where n is the length of the pack, right? So we need some way to do that. Then we're just going to use std sort with some sort of magical predicate that invokes this key function. And then we're going to get the type at each index in the sorted array of indices and use those types to form the resulting type list. So I'm going to go through that exact flow again, but I'm going to use the terminology of value domain and type domain so you get some idea of what's going on here. Okay? So in other words, we get the indices for our type list. So we translate our type list from the type domain to the value domain, right? We use std sort, which is a regular function, so always operates on the value domain, even if we have it being const_expr. It's compile time sometimes, but it still operates in the value domain, right? And so this translation between the type domain and the value domain is actually the tricky part. And the key helps us form a sort comparator that relates the indices in the value domain to the types in the type domain, right? So it's using the logic of a value domain sort for a type domain purpose. And that's because our key effectively takes a type and returns a value, right? So that's a very direct way of translating from types to values. Now, actually, when we call our key, we're passing an instance of a type identity, right? But the information we're passing to the key function is the type. And we're getting a value out via return. And then we translate these sorted indices, which are value domain, back to a type list, which is the type domain, by indexing into the original list. And then that's what we return. Okay, so let's jump into the first one, and then I'll ask for questions if people understand. Okay, an hour remaining. Awesome, which means I have ideally 15 minutes to hand off to Kris. I don't think I'm going to quite get there, but I'll get there before the hour like I promised. All right, so get the indices for our type list. This is std energy sequence. It was added in 11, I think.
14.
I think index sequence was added in 14. I I may be right. I think it is. I think it was added in 14. I think you might be right. Yeah, integer sequence was added in 14. We also added these helper alias templates, index sequence, which basically, so integer sequence is basically like integral constant, but it takes a pack, right? It gets a type and then a pack of non-type template parameters, right? Index sequence is a slightly more specific version of this that just assumes size t here, right? Because indices of things are size t's in C++ for better or for worse. But, maybe we'll get a S index sequence sometime, and that'll be like S size t. Never mind. It's a good joke if you were involved in WG21. Make index sequence is another helper template that's actually often implemented. You could implement it in the language. It's in the standard library. It's often implemented as a intrinsic, which means it's relatively fast in most compilers. And then in index sequence 4, which basically turns a pack of types into a pack of indices for those types, right? Which is what we're looking for. C++20 gave us one more tool for this, which we've already talked about this tool once, right? We've already talked about how amazing this tool is, where we can pattern match on something, right? By explicitly specifying some template parameters and then putting something else here, and we're pulling out this parameter pack from the value parameter to the lambda, right? We're pulling out indices. I'm going to pronounce IDXS indices because IDXS is, but I might switch back and forth. Apologize. Probably should have just used something else. But that didn't even occur to me until right now, so that's kind of awesome. But basically, right, we're passing an instance of index sequence 4, which is an alias for index sequence. And then we are deducing IDXS as a template parameter to this lambda. And that gives us a parameter pack that corresponds to the t's. And we can expand these together at the same time, right? We can expand args and indices at the same time with the same fold expression, for instance, right? This isn't really a cute trick. This is like the expected use of index sequence. Hence the name index sequence 4. I went into more detail on this in my CppCon 2021 talk. Those are the links if you want to take a look at it. Here's our progress. We've gotten another name, right? So if you ever want to try and go about trying to metaprogram yourself for fun, which I totally recommend, a large portion of what I've learned about C++ has come from messing around with metaprogramming. The way to start, it's like super overwhelming if you just try and dive in and you don't really have a strategy to break things down. And every metaprogrammer I've talked to, Kris, Eric Niebler, Louis Dion, we all start by just trying to get names for everything and then start adding the logic for those names. And so now we've got a name for these indices that we need, right? And so now that we can start naming things, it's a lot easier to start writing these algorithms. Does anyone have any questions? Awesome. All right. So we have a problem now. So we have our pack of indices, but we have a problem that stdsort doesn't, let me make sure I didn't skip something. No. Okay. We have a problem that stdsort doesn't return sorted indices. It'll be pretty clear in a minute why this is a problem. But
it sorts in place instead of returning?
Exactly. It sorts in place. Stdsort sorts in place, right? Which means we need to be able to do something like this. But in order to use these sorted indices inside of a type list construction, it has to be const_expr. So how do we work through that? Well, we use this immediately invoked lambda idiom, which you've probably seen in a number of other talks. It is far better explained in Teamer's 2022 CppCon talk. There's a link there that jumps right to the part of the talk that talks about the immediately invoked lambda idiom. But basically, this allows us to make this sorted indices const_expr and still have its construction span multiple lines. And this gets used all the time in real code also, right? Not necessarily for const_expr, but for const. If you need something to be const over its lifetime, but it has some sort of initialization sequence like this. This is actually a really useful idiom, right? And it's you can recognize it by this at the end here, right? It's a lambda that doesn't take anything, and so we call it with open close parens, and we get back something that can be part of a const expr initializer. I think I also talked a little bit about that in my CppCon 2021 talk. There's some really useful things you can do there with that. All right, so the thing we've added is this. Do people follow that? All right. Now we sort the indices, right? This is exciting. This is what we've been after, right? So we can stick the indices in an array, just using std array, using cited, right? We don't have to give a length or anything like that. We could do that, but std array has class template argument detection, and this just works, which is something people should be doing more in real code, right? They should actually be using cited with arrays. So it's a free little extra thing here. And std sort. There we go. Actually, we can do better. We can do std ranges sort, and we can avoid this whole begin and end thing. But either way, right? We're using a value domain algorithm pending this magic ... And that's what the rest of my part of the talk is going to be about, is this magic ...
The comparator.
Yeah, the comparator. And it's not simple, but it is not above the head of anyone in this room, to be clear. The question is whether or not I can explain it fast enough. So this is the part we just added, right? And, okay. So, oh no, we're missing one more thing before we do the comparator. We're missing this ... here, right? Once we have the sorted indices, how do we get them out, right? We have to get them out and put them in a type list. And to go from an index to a type in a pack, you need an @meta function, right? In value domain, we would use square brackets for this, right? But in type domain, we actually don't have anything that simple. Why we don't have language syntax for that is like a very often asked first question of someone coming to the C++ committee, and then they realize how much work it is to add something very trivial to the language, and then they decide it's not worth it. Common story. So we just use this. This is what we have. There's a lot of different ways to do this. Kris went into amazing detail on this last year. I really recommend that talk. It gives a lot of overview of not just the mechanics of writing metaprograms, but of using them. And it's just a fantastic talk. My CppCon 2021 talk also touched on a really cute way to do this that you shouldn't do. For completeness, here's a compact way to do this trick. You just can use tuple element t. Who's seen this before? All right. Who's seen this before? Why do we use the first one and not the second one? If we're going to go for something that's really slow, we might as well use variant. I don't know why we don't use the second one, but I thought that's pretty funny. Like I've seen variant alternative before, but I've never seen anyone use it for an @meta function. So I thought that was kind of a cute joke to put in there. Anyway, so just like regular functions, we can, so I guess there could be a progress slide here. Everyone follow the fact that we're not going to talk anymore about this @ function and what it's doing? Okay. Now we're just going to try and apply @ for each sorted index, right? Which is part of our implementation plan. We're going out of order a little bit because we're saving the hard part for the end, but that's usually what I do when I write metaprogramming code. So I try and save the hard part for the end, do all the parts that I already know. Kristen, did you have before we start?
Well, it's not like specific about any of the piece that you just explained, but how do you validate that this works? Like, how do you validate each piece works?
Static assert.
Okay.
You can do all of your testing with static assert.
Okay.
Or if you're like Kris and you want to be really fancy, you can show that the type and value domains are all the same, and you actually just use a regular testing framework and pass in runtime things and compile time things into the same test just to show how amazing you are. And also like to push like thinking about C++ forward and like do some really useful stuff, not just to show how amazing you are. But that's in his slides. I won't spoil that. but there are a number of ways to test this stuff. So normal function, when you have a dot, 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 right? Normal function call, I think most people in this room or at this conference have seen something like this before, right? Where this one dot, dot, dot is expanding two different things at the same time, right? It's expanding the type pack args and the value pack args, right? And that's by kind of looking back through the expression before this. Is a little more precisely defined than that, but go with my hand waving. And finding the unexpanded parameter pack. So you don't have to have the dot, dot, dot right next to the parameter pack, right? And we're kind of used to that. But then when you try and do it inside of a meta function, people get scared. They're like, dot, 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 angle bracket, dot, 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 angle bracket. I'm never writing C++ again. Right? Like, how many times have you seen someone complain about that on Twitter and be like, oh my gosh, there's 6 dots and 8 characters. I'm not writing C++. But we can break this down. It's actually not that bad, and it's pretty similar to this kind of use case, right? So we have 2 different packs in here, so that's going to make things a little bit more complicated. Conceptually, the compiler expands only unexpanded packs with the outermost dot, dot, dot. So it's conceptually like before doesn't really make sense inside of a compiler, and the standard doesn't actually say this. But conceptually, it's expanding before the innermost ones before the outermost ones, right? And then the outermost ones expand only the remaining unexpanded packs. So how do 2 pack expansions interact with each other like this? Let's walk through this example with like this case here, right? This really simple case here. Like T's is int double char and indices is 0, 1, 2, right? So first we're starting with this, and conceptually the compiler is expanding it to this, right? And there's still a dot, dot, dot there, so it's going to go searching backwards for the nearest parameter pack, and that's indices here, right? And it's just going to stamp out copies of this whole expression or type for each entry in IDXS indices, right? So we get this. And that's the full expansion if we were to make this substitution. Did everyone follow that? I think this is one more slide and then we'll do a progress and check in, right? So now we can do this same thing, but with sorted indices, right? Because sorted indices is const expr, we can move it up into these angle brackets. And it's the same thing we did before on the previous slides, but instead of expanding just indices, we're expanding sorted indices and using a square bracket to access into that array, right? All right, progress slide. Did people follow that? Awesome. Now the part you've all been waiting for in 10 minutes. Did you have a question? Okay. All right. So the value domain compare argument to std sort is a function that takes 2 elements of the range and returns true if one is ordered before, if the first one's ordered before the second one, false otherwise. So remember how I said, like, when you're writing a program like metaprogram like this, write the easy parts out first, right? So we have a signature. We know what std range's sort is looking for, right? We don't know how to fill this in yet, but we have a signature. And what we'd like to do is to basically call the key function with std type identity at I and at j, and then just compare them. Unfortunately, we can't do this, and that's for a number of reasons, but one of the main ones is that effectively that C++ doesn't have const expr parameters. And it's not a matter of like somebody sat down at the committee and was like, I'm just going to drop this from my paper because someone will do it later. And we've tried. We've tried very hard to get something analogous to this into the standard. And it just messes so many things up that it's not coming anytime soon. Maybe with full reflection or something like that. Do you mind if I wait until the...
It was about it's fine. I think I know the answer to it.
Okay, awesome. And I'm happy to come back as soon as we hit the next slide. I just really want to get this stuff in because I think this is really cool. So this is what we're effectively doing here, right? Where we want to try and effectively do this, but it's not It doesn't compile. So this is kind of a specific case of a more general question. How do I turn potentially runtime information, right? Parameters to a const expr function are potentially runtime information. Into compile time information like non-type template parameters, right? So we're turning something at runtime into a specific type. Something that's potentially at runtime into a specific type. Does that sound familiar? Right? Okay. If you're not understanding what I mean by potentially compile time or potentially runtime, I have a slide that goes into or a talk that goes into that in much more detail. Take a look at that. I think hopefully it's pretty well explained there. But the takeaway from it is that const expr doesn't really mean this will be evaluated at compile time. It means maybe it might be evaluated at compile time. Yeah, so in normal code, when we're trying to go from some runtime value to a specific type, that's basically runtime polymorphism, right? That's what that is. Here's an example of how we would do that, right? We look at some sort of tag, we do a switch statement, and we cast. Unfortunately, we can't do switch statements with parameter packs. We can't expand a ... over a parameter pack. This is another example, right, of converting information between the value domain and the type domain. It's an example of how important it is to understand the difference between the value domain and type domain, even in regular programming, right? It really helps you understand polymorphism better. Variant is another way that we can do this, and variant, conveniently, works with parameter packs, right? So, strategy. We create a variant of all of the types that we might want to call the key function with. That looks like this, right? Remember, we're calling these with std type identity, not with the actual t's, because some of these t's could be void or all kinds of other crazy things. And this ... here expands the type of the whole, stamps out copies of this thing, right? It's probably the way that we should say it. And we can make an array of variants that are initialized with an instance of std type identity for each alternative of the variant, right? So this std in place index t constructor for std variant allows us to do this. It basically takes the first argument and then a variadic pack of arguments and calls the in place constructor. Here our variadic pack of arguments is empty, so we're calling the default constructor, which works with std type identity because std type identity is an empty type. It has a default constructor that's pretty simple, right? Anyone want to guess why I use std in place index t here instead of std in place index? Because there is a value template, variable template, in the standard library. Anyone want to guess? Compiler bugs. If you remove this open close curly brace and you take out this _t, the compiler says, well, when I wrote this 6 months ago, I think it's been patched since then. The compiler says, and I quote, can't use IDXS that's not captured in this lambda. The compiler is very confused about what's going on. Okay, we are firmly in the realm of dragons. So just as a cautionary tale, sometimes when you do this kind of thing, you have to make really ridiculous changes like this, and things just work. So, cautionary tale.
Which compiler is that?
That was, I want to say Clang 13 point something. I think it was Clang 13 trunk when I was writing the, yeah.
Aren't they meaningfully different? Like the
No.
std in place index and std in place index?
Std in place index is a const expr value
Okay.
that is defined to be a default constructed std in place index t.
Is it like just, yes, so it's just like integral constant, but you made separate so that it won't be confused with other variants?
Yeah, it's an index. It's a tag type for constructors. We can't, because constructors, you don't know which one you're constructing if you want to in place construct a variant. And then we can just use visit. And we have effectively called the key for on the I element of the array, right? So we're done, right? We've constructed a way to do this, right? All we have to do now is just do less than. So did people follow that? Are there any questions at this point? I'm going to give myself 4 more minutes. Is that okay? And then go to your talk. Go ahead.
So the issue here is that, what do you call it? The actual parameters to this lambda are not considered to be constant expressions. And so we can't pass them into the template itself. We can't parameterize a template by them. And so we instead take the approach of kind of like combinatorially stamping out all the types inside of a variant. And then even though all of this is probably actually happening via const expr evaluation, we kind of trick it into saying like, okay, now we're doing this as like a runtime thing via std visit to actually pull out the type that we want.
Well, a const expr value thing, right? Because a const expr value thing can be runtime or compile time.
Right.
Right. But yeah, we are tricking it into saying that we're going to do this in the value domain.
So the key is like something uses overloaded, right?
It's passed by the user, right? It's a way of.
Yeah, it's basically like a few lambdas.
Right. It's a one-sided compare function, right? Some sort functions use keys, some sort functions use compares. Kris?
Can you just do a quick overview of the stuff you've explained so far? Is that too much?
That's it. This is all of the stuff I've explained so far.
Yes, but with words.
Oh, I'm sorry.
You can say no. We can do it after.
Let's do it after.
Okay.
I'm sorry. That was the talk, right? That was.
I know, just like a summary.
He's asking for a recap.
I'm trying to figure out how I would even recap this. Okay. So we get our indices that correspond to our types.
Yes.
We sort the indices with std sort, right? Because we stuck them in an array. And we use this this comparator that we wrote that uses a variant in order to actually call the key function on the underlying type that corresponds to the type identity at the particular position, right? So we're stamping out instances of type identity for each t, right? And then we passed that via visit for the ith one and the jth one, and we're comparing the results of evaluating the key function on those things, right? And that gives us a comparator to sort with, and then we can use those sorted indices to reconstruct type list with the types sorted. All right. I'm not going to get much time to go through this, but really quickly.
Could it have made sense instead of creating the index array outside of the comparator, the variant array inside the lambda, just create a variant array, and then somehow they have the comparator instead of accepting 2 size t's, accept 2 variants and run visit on them?
There are several other ways to do this, yeah. There are several other ways to do this. You cannot capture this, to be clear. This is not, you can't do captures in unevaluated context lambdas. But here's another way we can do this, really quick.
You didn't capture the, okay.
Yeah, sorry, I'll answer offline afterwards if that's okay, right? So we can create a jump table, effectively, right? Sometimes compilers, when a compiler has this kind of pattern with a large enough number of things, we can create a jump table. A jump table is approximately an array of function pointers. If you're a compiler writer, you can come get mad at me afterwards. But for the purposes of this, right, what if we created an array of lambdas that are calling the key function? Well, all of these lambdas are different. How do we make them into something that we can make into an array? We could cast a common type, which looks super ugly, and I'm not going to go through. Or we can use unary operator plus to decay a function pointer, and then these are all common type of function pointer, and so they can be ctatted into an array. So I'm not going to stop and explain that because I want Kris to have enough time. Another option here is what if we didn't want to assume a common type? Well, we can do a kind of product-like expansion of two packs, in this case, the same pack. This is another common metaprogramming trick where we have an inner lambda and we kind of get rid of one of the names by passing something in to the inner lambda from the outer pack, right? So we're like eliminating one of the names so that we don't accidentally expand it in this expression and we can expand the other expression. So I know that didn't make sense because I went really quickly. And finally, if we wanted to have a compare predicate, this is how we would do it, basically the same thing, by giving a different name to the outer parameter pack and expanding it. Sorry if that went really fast, but I want Kris to have enough time, and I've already taken way too much of his time. Yeah.
So wait, so at the end, at your last public slide, you basically showed us how to do like one way to implement, and then since then you just showed like a few optimization tricks.
A few other ways, yes. A few other approaches to this that you can learn different things from. So did you have a quick question?
Yeah, so assume that stud sort has annual again complexity.
Sure.
What is the complexity of this thing? Because looks like we are doing a lot of stuff with creating indexes and etc. that could increase the complexity, or it's still annual again?
It's compile time, so it's 0.1.
No, but it's still, I mean, we have to wait the compiler to run the thing. And
So Kris is actually going to talk a little bit about the efficiency, so I don't want to take away his thunder, but I think you'll be surprised. That's what.
Okay, thank you, Daisy. I think that was awesome. Right now we can actually get to template metaprogramming. Just kidding. Just you know, I know template metaprogramming, a lot of templates might be kind of overwhelming sometimes. So just to make them less scary, let's start with a joke. Why did C++ template class refuse to go to the party? It would be a lame joke, by the way. Because it didn't want to be instantiated with the wrong cloud. I like that. That's the crowd. Okay, so moving on. Why we would do that, right? So Daisy explained perfectly what we can do with the sort function, by why we would go about it. So if you have a struct, which is, for example, not aligned here, anyone, what will be the size of this guy accordingly to the standard when we have to have the alignment requirements satisfied?
12, 16 bytes. 12 bytes.
Around 12, 16?
Yeah.
Yeah, more like 12, yeah, on x86, yeah. So that's obviously not the most efficient way to align those things. But if you have the same struct, and if we try to align it, we will get the size of 8, because that's the minimal alignment for those guys. And how to do that? Well, the way to do it is to sort it. Why? How we do sort it? Well, we had the talk about it. So as simple as that. So we will get align. Here we have a function. We will explain what the tuple actually is doing, and then we pipe it to the sort. And that's what we will talk. The second part will be about. So this pipe operator is the magic, which we'll try to explain here. But you can imagine how powerful that is. And that, why we would do that? Because that will give us performance, that will give us better memory layout. And it's cool. So is that clear? Is that cool? On the same page. Okay?
So you do like using like a type def for the result of this thing in order to actually have a struct that is aligned that way?
Yeah, so if you sort the fields inside the struct in the order that they are sorted, like in the descent or like order of the size, then the size of will be the size of the alignment of each thing, if that makes sense. So this is the almost standard compliant tuple, which Daisy has an awesome talk at CppNow. But if you have a struct with the end and foo, and we would like to get a tuple, because we have to have the fields out of it, we can implement it the following way. We have the tuple, and then we get the const expr if with the requires clause. When we have the structure bindings, we get the elements, and we create the tuple. So we can do that for many different ends. Anyone who is, which part of that is not standard compliant? I know Daisy knows.
Does this only work for aggregate types? That's my only real guess.
Well, that's for aggregate types. Yeah.
Yeah.
But that's compliant
That's
still.
compliant.
The part which is not compliant is requires the structure bindings part. That's awesome. It works in some compilers, but it's not standard compliant. There are other tricks to do it. One of the tricks is just to use any type that is with implicit conversion operator, and then calculate the number of fields. That's also
The
a way.
body of a lambda is not an unevaluated context for the purposes of concepts. So we do that.
Right. Okay, so let's try to dig into what we can do actually with leveraging the sort and other algorithms with the ranges. So let's call it template metaprogramming, which is not actually metaprogramming because there'll be no much angle brackets. That's the goal of the talk. We'll limit the angle brackets right now. So this is powered by this library. We can check it out. And let's take a look into an example. I'll try to compare MP11 and this library to compare how we can actually do that, and also the SDD ranges. So let's introduce a command which has a name and the ID. The name will be identified by the start, add, modify, and delete commands, and the ID will be just some special identifier for that command. So right now, we'll implement a test case for it. Imagine that we have a vector, const vector. There's no const expert here, although it's C++20. We don't have to do that, which has some commands like start, add, modify, delete, with some IDs. And then we'll call execute, which we'll explain in a second, with some predicate and some operation in which we'll get the modify and add. Any ideas what kind of algorithms we can use here to actually achieve from the top of the slide, the bottom of the slide? So we have an add and mod, and we'll have to manipulate this vector somehow. So just to help, because I don't have too much time, there'll be a lot of transform, filter, reverse. There are a lot of ways, obviously, to achieve that. For loop, raw for loop, not preferred option. So how we do that in C++20 ranges? Well, we'll include ranges. 8 seconds later, or 15 in GCC, we'll get the following implementation. That's not the most efficient implementation as well, because maybe the order of operation might be different. But who understands this code? Like, who can follow what's happening here? And who could follow the sort before Daisy explained that? So yeah, in my opinion, there's a difference here. I think this code is really expressive, but it's runtime. So if it comes to the predicate and this operation, the predicate is just getting the ID, which is equals to 2, and the name, we just remove the ID, which was then set. So for our vector input, we remove the start. After that, we reverse. We filter the ones which have 2, and then the transform ID to 0. It's not really important what it's doing. It's a cool way of doing that in C++20 with ranges. I really like it because it's really expressive and declarative. So let's do it at compile time. Who has been to Jody's talk for about MP11? OK, so I won't be going into details because you can watch that talk. But how we go about going from runtime to compile time. And why we would do that? Well, basic performance. You can imagine that we have commands which are coming in, and you can extract some patterns at compile time, and you get the performance using some jump tables on stuff like that, which is usually happening in the compile time. So if you go about it, we have a command which is at runtime, right? So it has a string view name and ID at runtime. And how we would switch that to compile time? Well, if we do not use NTTP, which is also an option, however, it has its own limitation. For example, MP11 doesn't work with it. The fixed string would be an option to get the name. Who is familiar with fixed string? That talks about it. It's basically the idea that we can pass the string. string into the template, which we couldn't do before C++20 unless we will use GNU extension or something like that. So the idea here is just to clarify, we get the names from fields into the template classes, right? Nothing really special, but we need that. Okay, let's take a look into the MP11. We apply here TDD, so we always start from the test. Instead of a vector in the template type list word, we will have MP list, and MP list is just exactly what Daisy explained with the type list. So it's just implementation in MP11. So instead of vector, we have commands with the following same elements. Expected will be kind of the same, just another MP list of things. And then we would, instead of having an expect or requires or anything depending on the framework you're using, we'll just do static assert. So that would be our expectation. And just a small remark about type ID. Type ID is const expert in C++20, which I find very powerful. Who is using this way of comparing? Yeah, it's same, very popular. C++20, same as concept, kind of nicer, slower to compile because we have two sites which are being compared for a really cumbersome reason. I won't be getting into that. But what about that? In C++20, we can do type ID of int equals type ID of int. And what is cool about it, actually, if you have a value, which is important in our talk, is the fact that we can compare that as well. So type ID 42 is an int equals type ID of int equals int. So that's concise way of comparing types.
And will this be true? So this will be true? So type ID of a value is
yes, that will be true.
Type ID of
Yeah, all of these static asserts will pass. Okay, who can do this example in MP11 just like that? Okay. That's it. I'll go for it. So there are familiar names here, which we used as well with the ranges. So MP transform, MP filter, underscore Q, because it's a quarter meta functions, that's not that important, MP reverse, and MP drop. We can kind of have to do it from the bottom to the top. There are other ways of achieving that, but that's kind of the simplest way to go about it. So we have to have this predicate, so we have to implement the meta function, which has this fn. We have to know about it and compare the IDs. And then the operator will just create a new command without the ID, which means that the ID will be 0. So that's a quick way going about MP11. One of the problems, in my opinion, here is the fact that this predicate and the operators have to be outside of our meta function, and that's because of the template metaprogramming. We cannot apply really lambdas. That has, some positives because we put a name on thing, but it also negative because sometimes like the command colon tname would be nice to just put inside. So who is following MP11 code? Makes sense. Question?
Do you use MP compose?
You could use MP compose. You could. There are tons of ways, and as I pointed out, Jody has a great talk about it to achieve similar thing. I just wanted to have the MP transform, filter, and reverse being seen here, and pointed out that it's actually very similar, which I think MP11 did a great job. It's default go-to for the metaprogramming these days, but it's different. So if you compare the STD ranges solution to this solution with MP11, I don't know, I can go slower, but I don't know do you see the difference? Anyone see the difference here? Well, I see as well. Just for the record, everyone see that. It's a bit different. It's close, but it's a bit different. We can kind of try to manipulate it a bit more with the MP compose and stuff like that to get it closer, but we'll never get to the runtime thing, right, with that solution. But maybe we can. Can we do better? And that's where, all this talk about the sort and ranges is coming to to show its promises. So with the MP library, we can actually do something very similar to what we did with the MP11. So we have MP list, which has the commands. MP list is basically a variable template of a type list because we want to be in the value space here. But besides that, it's just a type list. There's nothing really special about it. Besides that, it's a variable template. Everyone familiar with variable templates? Yes. So then we can do static assert. So we at compile time world, we have this MP list of these commands transformation which we are going to apply, and we call this execute. And I don't know whether you can notice, but this execute is very similar to what we actually had with the ranges at runtime. We have the v, which is the variable template of the MP list, not of the vector. We have the predicate and this operation. So I hope you know where that's going. And that will be the implementation. So the implementation here is very ranges-like because it actually is using ranges. The only difference is the fact that we have this 1_c. Why we have that? Why we need that? Well, I gave an answer, so I'll just check in. We don't have context for parameters, as Daisy pointed out. And because of that, we cannot really do that at compile time. And this 1_c will produce as an integral constant, which we'll see in a second. The other difference between this solution and the runtime solution will be the fact that our predicates will be different. And they will be compile time things. We could, if you have constructed parameters, make this code exactly the same as runtime, because this 1c would go away, because it will be compile time constructed parameter, and we could apply NTTP to have these predicates the same. But because we are in type list world, we have types, and we have to therefore apply the C++20 lambdas with the angle brackets. Everyone familiar with those type of lambdas? Notice that we don't have to have parameters as well, which is kind of cool. So the T will be our command at compile time, and we have comparison to ID, and then we produce a new one. Make sense? So just to remark the constructor parameters. The reason why that doesn't compile is the fact that the v here, when we try to call the foo, is not a constant expression, right? It's a runtime expression, and therefore we cannot create, in that case, an array with the v. But there is a way of doing that. Any ideas what we can do to avoid that compilation error?
Non-template parameter.
Non-template parameters. That's a solution which I'm not showing any other solution, but it's a good one.
You had that _c.
Yes, yes. Underscore c, which is actually expanding to integral constant. I like that. So this 42c is actually a UDL, which will parse the characters, and in the end, it produces the integral constant of type int, let's say, and 42.
UDL is user-defined literal.
User-defined literal. Thank you. So this v in that case will be the integral constant, a type. It won't be a specific value like 42. And then that has the implicit conversion to a value, and the array will take that and will be satisfied. So when we have that, and we'll do the same comparison, we will get, and wait for it, this. Is that closer?
A little bit.
A little bit closer. So let's take a look about the differences. So one difference is this 1_c, right? Because we don't have these constructed parameters. And the other difference is the fact that the predicates are different. But I think that's OK, because we actually in template world, right? So we have the same meta function, this function execute, and all the algorithms are the same. However, what we'll be passing through depends on our context. if it's a vector, we'll have predicate on objects, and if you have type list, we'll have a predicate on type list or types. So this difference is not that bad, in my opinion. The other thing which we can do, actually this 1_c will work at runtime too. So if we have the runtime being changed, we can go to, question?
Yeah, I was going to say, so I guess it took me a minute. So the main thing that makes, what do you call it, the _c work is the fact that it has, so you end up passing it through as a type, and then it has a context or implicit conversion operator. Okay.
Yeah, exactly. So just to rephrase, the integral constant has the expert implicit conversion operator to underline type, and therefore that works with the array. Yeah, thank you. So just to point out the _c, with the _c, we can actually apply that at runtime because this integral constant will work at runtime. There's nothing really stopping us. So if we really want to change anything, we can change the runtime, and then we'll get to that.
Because views drop also accepts like an int and then
Yes,
convert.
exactly. The drop and all the views accept the template, which has to be, there is a concept there which has to be integral type, which will be satisfied because of the conversion. So I think that's pretty cool because we're really close, and one of them is template metaprogramming, and the other one is runtime. So that's pretty cool. So how does it work? Daisy already explained most of it, so I won't be getting into detail that much, but I just wanted to show the addition of the ranges which makes all of that possible as well. So imagine that we have a tuple here, and we would like to filter the types which have the field B in them. Maybe not a very common case, but I wanted to point out here that you can actually use the lambda with requires, which allows you to do a lot of magic. Under the hood, you don't have to have concept, named concept to do so. So what we do here is we have a tuple of foo, bar, and buzz, and then we pipe, and this pipe will be the magic to a filter, and filter is just the range function. Make sense? So that's how we will go about. So how we start? Well, we have to overload the pipe operator with a few templates. Not so scary, but let's say we have this template for the TSS, that will be the tuple in that case, but you can imagine type list or anything else which has types. And the other part, which can be done many different ways, but to simplify it, that's just exactly what lib C++ actually is taking. So it's a range, which will be adapter of something, which will take, the A will be the adapter, which will be the filter, the T will be the tuple, and Fn will be the lambda. So that will be the return requires. Make sense so far? We try to overload that, and then we have these requires to not to overload it for everything. We only care about our use case. So isEmpty_range is a concept which verifies that we are in the template world, so that we don't have to. We want, we don't mess up everyone else's code. So what we do here, we try to get the functions, the predicates. So we get an array of functions, and we call the operator with the TSS. And everyone familiar with this weird syntax for calling lambda, which has just angle brackets? Because we don't have parameters, we have to do template operator. Thank you, C++. So that will produce false, true, true in our case, because foo doesn't have it, and bar and buzz has the B, right? So false, true, true. The next thing we do is we take the ranges, because we're in the ranges world. We take iota, which will give us the IDs, 0, 1, 2. We call this adapter, and here is the magic. So we don't really care about we don't have to implement that filter, right? This filter is implemented inside the ranges. And we just say which ones are satisfied. So which ones are true, which ones are false. And then that will actually, what is really interesting here, because when you had the sort, the number of indices was the same. Here, the number of indices will be actually less, because we filtered it. So we have 0, 1, 2, and after that, we'll get 1 and 2, because the 0 will be filtered. And when we do std ranges too, we have to do that to static vector because we in consexpr context, so we cannot use std vector from C++20, although it's consexpr. But static vector is just a simple array with pushback. And then, as Daisy pointed out, we do this immediately invoked lambda with make index sequence. We get this index sequence. The T is a tuple, so we create another tuple of the type. We do get, and indices is something which we already populated. So the size of the indices will be 2 because we filtered. And ISs will be 0 and 1. We get indices from 0 and 1, and that'll be 1 and 2. We get it from the initial tuple, and we get the bar and bars. Make sense? I hope so. But that's the underlying implementation, yes?
Just as a quick refresher here, what is A again?
A is an adapter, so in that case, it will be the filter.
Okay.
And you can imagine that's kind of generic when you look at any other function. Whatever the implementation at runtime in the ranges is, will be just.
Right, and T is the tuple in this case.
T is in tuple. And just to remark, this implementation is not exactly like in the library because it's specific to lib C++. In lib standard C++, the T range A will not have the T. It will be just fn. But that can be overcome by using the value type of the T. OK, so I hope I managed to convince you a bit that this implementation is actually pretty cool. Who would be able to do metaprogramming with ranges? I think everyone. Well, if you can't do the runtime as well. So I will question your skills.
But basically, are you saying that the only missing part was the pipe operator?
Yes. Yeah. Basically, yeah. So just to repeat the question, the point being made is that the fact that if we actually add the pipe operator, we can do all the magic with ranges on top of that. Obviously, we need C++20 and other things to make that happen. But yeah, basically, yeah.
Will we add it to the standard?
Can we add it to the standard? Wow.
Can we add it to the standard? Well, if anyone from the standard, Daisy, we can talk about it, definitely. So what about, because it's awesome, in my opinion, that we have that for type list and the vector, but can we do more? It's like there's so many other types in C++. That we have NTDP, we have variants and things. So let's just give another example, which will be just a slice. Slice is implemented in ranges, but we will just re-implement it. We just drop and take with the pipe operator. And notice here we have this 1C, which we have to subtract from end. But yeah, that's what we have to do. So that will work on the type list. Easy, right? We've done that already. We have type list of int double float short. We slice it, and we get part of it. Easy peasy, right? But we can do the variant as well, right? That will work. That will work also with MP11 because we still have the types. Sorry. But what about that? That's something which won't work in MP11 and will just work in this solution because it doesn't really matter what it is in that case. So the values. We have a list of 1, 2, 3, 4, and we would like to slice that. Still works. And we are in the template world. Fixed string, as pointed out. That's super cool in C++20. We have foobar, and we would like to slice it. We can do that as well. And there's nothing really special here, so I'll just go and go and go, because that's super cool. In my opinion, one of the best things about it is the fact we have a tuple here of values. And we can actually, at compile time, extract the ones which we're interested in. So there's no 1C here, 2C, or anything like that. It's just values. We can slice it as well. And finally, we can do a runtime. There's the same function. There's nothing really changes here. Nothing really changes here. It's a tuple of some runtime values. I put the argc here to to make that obvious. And it still works. So in my opinion, that's super powerful because you don't repeat yourself. And we can do, especially the testing. So that's one of the main problems. There was a question asked, how we actually test that, right? Imagine that we start from runtime, right? We start from runtime, we do the ranges, we can debug it, we can test drive it, and then we just put the type list on it. There's nothing really special about it. But you can ask, Jody?
Yeah, so the mixture there on that back one, where you got the tuple of actual, those are runtime values being split with the compile time constants, right? So you're merging the two at compile time to try and determine which one, what you're going to have, right?
Which case are you talking about? The third one?
The
last one.
Yeah.
This last one actually doesn't require this 1C and 3C because it's runtime. So we can do 1C and 3C.
Well, so there's a technique with using an MP11 map to map from one type to another and have those types be the elements of like a tuple, so that you can at compile time just pick which item you want for runtime.
Mm-hmm.
But it sounds like that's what this is doing pretty much by itself, right?
Yes. So there's a comment, MP11 is cool, but this solution is even cooler.
So let's say, I think I understand, but so let's say I have a vector. A vector is a class that has, it's templated on two things. And let's say that the vector is 7, happens to be of size 2, and I want to slice just one of them. The entire requires clauses that you had before, that's what makes it so it will slice the values of the vector and not suddenly try to create a vector object with different, like with just one template.
Yes.
Thank you.
Just a comment. So I bet you wonder, because ranges include takes a bit of time. There's a lot of concepts. How does it compile? So let's do the poll here. Who thinks it will be faster than MP11? Wow, I like the audience. Who thinks it will be slower? No one.
You wouldn't have shown that.
Well, we're showing it for correctness and like simplicity, not necessarily.
Yeah, you showed us like 500 lines of code. You're showing us the benchmark for like 1,000 lines of code. So obviously, it's,
All right. Who thinks it doesn't compile? Okay, so it's not as clear cut. So I wanted to point out the benchmarks, which are more than just one single meta function, because usually they're very similar and it's really hard to distinguish them. But when you try to do and pipe more, then you get.
Hey, Kris, I'm sorry. It's pretty small. Could you tell me what the X and Y axes are?
Okay. So the X is the number of elements, so from 0 to 400 types. And the Y is time in seconds. It's up to half a second.
Thank you.
And the colors are important. So the orange one, this guy is MP11, and this guy is the ranges. So as you can see, on the below 50 elements, the ranges is much faster, which is the common use case. I would say usually we have a lot of small, which we try to combine. But it scales pretty well. It doesn't go too far from MP11. And MP11, Peter did a very well job on optimizing it. And this one is just not optimized, like it's ranges. Wow. So for me, that was really impressive that actually out of the box, that was so close. But what was even more impressive is the fact that if we do, and orange is MP11 and blue is the ranges, when we do sort, pipe to unique, to reverse, that's one of the meta functions which I tried to test. That was really impressive how well it's actually scaled with the ranges. So for less than 20 elements, MP11 is a bit faster, but you can see how it scales not too well, and ranges do that I would say, amazingly well. And the reason being is that we do not instantiate much with these ranges, right? Everything is const_expr, and there's no instantiations. And what is funny actually, because who knows about template depth parameter? I have to change that to more than 1024. So that's common when you do a lot of things recursion with templates.
Compiler flag?
Yeah, compiler flag. There's another one for const_expr, which you can reach as well with the ranges. I don't remember. There are a few, because there is one also for the brackets, default expressions. But yeah, you can reach those guys instead of the other ones. So I hope that makes sense. And with that, yeah, let's embrace C++, template metaprogramming. Thank you. Question?
Yeah, I was going to say, so I did most of my template metaprogramming back in like 2018 and 2019, and clearly there's a lot of cool tricks in 20. Is this code available anywhere? Like,
Yes. Yes, there is. I can.
It's on GitHub, the
Is
links in the slides.
Okay.
I can go to it.
Yeah, I'd love to play around with it.
Yeah, there's full support. It's here. There's a full support of basically all ranges algorithm and a lot of examples as well. What can be done with it?
It's about 1,000 lines. If we were really trying to golf it, we could probably get it into 200 lines of understandable code.
Understandable code.
I mean, understandable if you can read the ranges library itself, right? It's not much more complicated than ranges itself.
Other questions? If not, okay. Okay, thank you.